Thanks for inviting me here. It's really inspiring to hear all these talks and just kind of hang on to your coattails and try to keep up. So I'm Simon Fraher. I did my master's and I'm working on my PhD at North Carolina State University with Craig Yencho in the sweet potato and potato breeding and genomics program. I'm just talking about sweet potato today. And I'm talking about marker-assisted and genomic selection strategies that we're trying to implement, again, following the footsteps of many of the folks here. Arrows clicking. Yeah, okay. Arrows. All right. So North Carolina produces almost 70% of the U.S. crop. It's almost all the variety Covington, which came from our program in 2005. I've heard estimates as high as 98% of the domestic market comes from a single seed back in 2005. Sweet potato is hexaploid. It has 90 chromosomes. It's sort of self-incompatible for the most part, so we can't really take advantage of back crossing. But we do get segregation at the F1 level, and because it's asexually propagated, one seed can become a major variety. Another implication here, we send about 40% of our state's crop to Europe, and that'll be important here in a few slides. We have three major diseases, well, four now in North Carolina. The guava root knot nematode is the latest addition. This is under internal quarantine. It was brought in from South America and it's been in the US since the early 2010s. That internal quarantine is a big issue for North Carolina because, again, we send 40% of our crop to Europe. And if it can't leave the state, that's a huge, huge toll on the farmers. So that's under quarantine. I talked a bit about that last year. We'll talk some more today. Southern root knot nematode is cosmopolitan in distribution. It's been around forever, and it's still of economic concern. We still need to have a variety released that's resistant to it, but it's not under quarantine. It's not as big a deal. Virtually indistinguishable in the field. And then I'm also going to talk about fusarium wilt briefly. We won't get into soil pox this year, but maybe a few years from now. So last year I talked about my work with the TB population, Tanzania by Beauregard, and we've heard some other folks mention that. Tanzania is a Ugandan farmer variety. Beauregard is what used to be the major variety before Covington. And this population segregates for a huge number of traits. It was created by some of my predecessors. And after the quarantine on guava root knot nematode dropped in 2018, or I guess was imposed in 2018, we started screening everything we could to see if we had any resistance. Tanzania happened to be resistant. We already had a population and we had a linkage map. So it was just a matter of phenotyping. Nice little master's project for me. And it turned out that it appears to segregate 1-to-1 for resistance, the progenies. So that's pretty good indication for us that there's a major gene involved, and that motivated a QTL analysis afterwards. And just the theory behind that, I know most of us understand genetics better than I do, but this is sort of a reimagined Punnett square. If Tanzania has one copy of a resistance allele and Beauregard has no copies, we expect half the gametes that Tanzania forms to have one copy. That segregation pattern will be 18-to-18 or 1-to-1, and that matches that 50-50 or 49-to-51 phenotype that we saw. We had, again, the TB linkage map available from my predecessors and the DC linkage map. I'll talk about that population in a couple slides. And these were both constructed using Map Poly 1, I suppose. These are a couple QTL that we discovered for root knot nematode resistance. So the first is for Meloidogiant incognita. That's the southern root knot nematode, the one that's not quarantined. Dr. Bonnie Aloka, who did his PhD with us, found that QTL on chromosome 7. I found during my master's a QTL on chromosome 4 for guava root knot nematode resistance, and they're both pretty highly significant. The MI locus, the heritability was like 0.63. The ME was about 0.7. So again, further evidence that we maybe have a major gene. My goal as a sort of applied breeder, or I'm training to be that, is not to identify those genes necessarily, but turn them into selection strategies. And so that's what we did. We worked with LGC, Biosearch Technologies. We also worked with Intertech on designing CASP markers for these two QTL. And essentially we went to that peak QTL position and selected a dozen markers on either side of those QTL. And we tested it. We have 3 markers now for guava root knot nematode. That's Enterolobii on the top. And we have 1 marker for incognita, the southern root knot nematode. For reference, the 3 markers on top all are more than 90% accurate. They range from like 95 to 98% accurate. And that's not just in those original mapping populations, but that's in really diverse germplasm from around the world. The incognita one is a little less accurate. It's about the latest update. It's about 75 to 80% accurate. So that one still needs a little bit of work. But this is really just an initial look, right? We kind of just picked 24 markers and tested them. We got lucky, but we got lucky twice. So the strategy could potentially work, at least with major QTL. And I should mention we use FitPoly. When you get the reads back from LGC, their software is designed for diploids, so we're able to make dosage calls with FitPoly. You can't really see, but that first marker for Enterolobii 123, there's 1 yellow dot there. So we actually have 1 individual that appears to have 2 copies. Back to our Punnett squares here. If you have, before I cut off a little bit, but essentially what this is saying is on the left here, that Tanzania type parent would have 2 copies, and you recover a higher ratio of resistant progenies. If you had 3 copies, the number is even higher. And if I could self that one with 2 copies and get 4 copies, on paper, you get 100% resistant progenies. There's a lot of other issues there, and it's not really that simple, but enrichment is one of the things that we're working on right now. I showed this picture last year, but we didn't actually have results back. I just sent the tissue off for sampling. This is second-year materials. Our pipeline's very similar to Jeff's, as he described. So we screened 200 lines from our second-year pipeline, and these were just lines that had a guava root knot nematode-resistant parent, or maybe 2. And we found about, in this set, I found about 17 that were resistant to both nematodes. Now, these are elite lines, but when you cross into a resistant background, it tends to be less likely to be selected because there's a lot of linkage drag and other traits you don't want that come with the nematode resistance. So I don't expect that 50-50 segregation here. And I tested those markers against phenotyping this set, and they're still holding up pretty well in our actual breeding germplasm. Switching gears, fusarium wilt. This used to be the biggest problem in the Southeast, but thanks to resistance breeding, it's largely been controlled. In fact, a lot of our growers aren't even really aware of it. And that's because Covington, which is maybe 98% of the market, is resistant. As I mentioned, we get linkage drag, we get traits we don't want. Most of the guava root knot nematode resistant lines that we're breeding with lack fusarium wilt resistance. And so that's kind of our next big step. 1 step forward for guava, maybe 1, 2, who knows how many steps back for fusarium resistance. And this is where I'll talk about that DC population, which we had the linkage map constructed for. This is DMO4 0001, circled in red over there. That's our susceptible genotype. And then Covington, which is our resistant genotype. And this population is about 550 progeny. We've lost a few over the years. When we phenotype for this trait, I'll cut the plant at kind of a 45-degree angle, and I'll look for vascular discoloration. And I'll also look, as the name describes, for wilt symptoms on the top. These are QTL from phenotyping the DC population. So on top, you can see there's 2016 and 2017. This was sort of a preliminary look at this by a master's student, John Kinchik. And then I replicated his assay with a little more nuance. And I actually didn't use raw phenotypic data. I used adjusted means. So I had accounted for who was rating the plants, plot structure, reps, that sort of thing. I still found the same major QTL that he did on chromosome 10, which was really exciting to see. I did not find the minor QTL he saw on chromosome 3, but maybe I found one on chromosome, 6 there? I'm not really sure. It does not appear to necessarily be a major gene, but we need to dig into this a little bit more. This is pretty new information for our team. But I want to use that same CASP pipeline and try it out. See if we can find some markers that are, greater than 70% accurate or better. Oh, and we used map poly again, QTL poly, and visualizations come from view poly. And lastly, I want to talk about our genomic selection efforts. So pretty much all the talks we've heard, you guys are several years ahead of us. We haven't actually applied genomic selection yet. We don't really have genomic data. I just collected tissue and it's ready to ship to DART next Wednesday. So we'll hopefully I can follow up with that next year. Our training population was created in 2019 and 2020, and we used a polycross nursery, which has some downsides. It's convenient, but you only know who one parent is because you're collecting seed from the maternal plant. Pollen could be from any of the neighbors. We used a mix of 11 parents. Half of these are major varieties or highly elite lines, and the other half are resistant to that guava root knot nematode. And we created this population before we knew or had good evidence that there was a major gene involved. We thought it was going to be a little bit more complicated than that. 33 families in total, so each parent was replicated 3 times in the nursery, and we had about 25 progenies per. That population ended up being closer to 550 genotypes. We used augmented row column designs to plant out those genotypes over 3 years. And most of us are probably familiar with this design, but essentially what we're doing is repeating checks in every row, every column, and within each block, so that we can adjust performance based on those check performances. So if these are 1 acre plus trials, if there's a flooded spot in that pink square in the top corner there, and Covington and Beauregard do really poorly, we can sort of adjust the performance of the other genotypes in that plot. And thanks to that design, we're able to generate BLUPs. I'm not going to try and explain this to folks who know much more about it than I do, but essentially, we don't have genomic data, right? We have an A matrix, but we only have half the pedigree available. And then we have all of the parameters that I sort of described in the augmented row column design. So we have our checks, environment, replicates. There were multiple different environments for these trials. Not pictured here as a year, but we have 3 years worth of data now, and then some nested effects. And this is sort of putting the handle on the toolkit, right? These are the outputs that a field breeder wants to see. They want numbers that they can use to make decisions. You do need to have that background knowledge as to what these numbers mean, though. So we have six yield-related traits on the top there, and then we can on the top, those are our intercepts or the mean of the entire population. And then you add or subtract your BLUPs from those mean values, and it gives you the individual's performance for whatever trait you're interested in. We're just focusing on yield-related traits because yield's probably the most important trait for us right now. But I'd like to explore, flavor, quality, disease resistance, that sort of thing in the future, once we're confident this works in sweet potato. So it's really nice to hear that it's working for all these other polyploid crops. And as I mentioned, we are just now getting genomic data. So we're working with DART, and we're being sponsored by Breeding Insight. We're genotyping the whole TB population, the DC population, our training population from 2020, and a sort of modernized version of that from last year that just incorporates more relevant breeding material. So we have a 3K panel, and it's polymorphic, distributed across the entire genome. We've heard a lot about these probes that other folks are using. And we're going to try out multiple different GS models. I want to dig into some of the other talks a little bit more, and probably you'll hear from me. I want to gauge how these other models work and apply them to sweet potato as well. And I guess one of the big points to be made here is that we're not trying to replace breeders. We're trying to give breeders a tool they can use to better facilitate their decisions. And this is one line that, as part of my dissertation, I want to compare breeders' decisions with different models, as well as with our phenotypic BLUPs, and see how well those things correlate. This GS203222 that's pictured there. That line was in the same block in the same trial as Covington and Beauregard pictured beside it. So that was a very easy selection for us to make. And it also was in the top 5% of BLUPs, at least the phenotypic BLUPs that we had. And then I tested the markers and phenotyped. It also has guava and incognito resistance I'm not sure about fusarium yet. But ultimately, that was the first time we were able to go from seed to a potential parent in 2 years, which is unheard of in our program. It usually takes 6 or 8. So this is really just shortening the breeding cycle, and I'm really excited to be sharing that with y'all. And with that, I'd like to thank a huge list of scientists. There's, I'm sure, many people missing from this list, and of course, all of our different sponsors and tools for polyploids. So thank you guys.